For centuries, the inner solar system appeared to be a perfect machine, a flawless, eternal clockwork with planets locked into endless, repeating loops. Modern orbital dynamics reveals a more precarious reality. While the giant outer planets are stable over billions of years, the terrestrial planets operate on the edge of dynamical chaos. We rely on the assumption that these orbits are inherently fixed and predictable. The Earth-Moon system provides the specific gravitational mass required to stabilize our neighboring planets. Without the presence of the Earth and the Moon, the mechanical stability of the entire inner solar system fails. Researchers Innanen, Mikkola, and Wiegert used the Wisdom-Holman symplectic mapping method to model this instability. They utilized self-consistent N-body simulations to observe how the inner system reacts when specific planetary masses are altered or removed. This schematic represents the baseline system: Mercury, Venus, the Earth-Moon system, and Mars, all following their standard, nearly circular paths. In these simulations, the Earth and the Moon are combined into a single gravitational entity, a barycenter, moving along this third orbit. The data shows that the Earth-Moon mass actively suppresses a hidden, destructive resonance that would otherwise be driven by the giant planets. Orbital stability in the terrestrial precinct depends on this ongoing gravitational damping. To isolate the effect, the researchers first removed the Earth-Moon mass and placed Mercury's mass into the Sun to simplify the simulation. This chart tracks Venus's eccentricity over 10 million years in an Earthless environment, immediately climbing to nearly 0.6. It fluctuates on an 8.1 million-year cycle. However, the lower panel shows its semi-major axis. The average distance from the Sun remains constant. An eccentricity of 0.6 means Venus transitions from a circular path into a highly elongated ellipse. With an orbit this stretched, Venus sweeps into the regions of space reserved for its neighboring planets. A second test restored Mercury to the simulation, while still leaving the Earth-Moon position empty. Now Mercury and Venus become coupled. Chaotic diffusion lets Mercury respond to resonances Earth normally suppresses. Its eccentricity spikes over 0.7, shown by the solid line, while the dashed line shows Venus's eccentricity being slightly dampened. Mercury's extremely elongated orbit now forces it to cross directly into the orbital path of Venus. This orbital diffusion leads to a powerful gravitational encounter. The planets deflect off one another, violently throwing Mercury entirely out of the solar system. Without the Earth to act as a gravitational buffer, Mercury is lost, leaving Venus to resume its highly elliptical, unstable path. This raises a mechanical question. What force is actually driving this chaos when Earth is removed? To find the source, the researchers cleared the terrestrial planets and seeded the inner system with massless test particles, leaving only the giant outer planets. The test particle data reveals a massive vertical spike in eccentricity, indicating a zone of extreme instability. That spike aligns perfectly with the 0.72 astronomical unit mark, the exact heliocentric distance of Venus. This is a secular resonance, a long-period gravitational effect orchestrated primarily by Jupiter and reinforced by the other giant planets. Over millions of years, the perihelion longitude of Jupiter rotates. At this specific distance, the perihelion of Venus begins to librate or sync with Jupiter's. When these two longitudes lock together, Jupiter's gravity pumps eccentricity into the Venusian orbit, stretching it further with every cycle. The Earth-Moon system sits in a position where its mass disrupts this sinking process, preventing Jupiter from locking onto the inner planets. Earth provides the gravitational interference needed to break Jupiter's grip, ensuring the inner system remains stable. While orbital stability is the baseline requirement for a planet, it is not the only factor in its survival. Over geological timescales, stellar forcing, the influence of solar wind and luminosity, dictates the ultimate lifespan of a biosphere. Venus serves as a case study for the effects of stellar forcing on an unshielded terrestrial planet. Venus lacks an intrinsic magnetic field. This allows the solar wind to interact directly with the upper atmosphere, stripping away ionized particles. Instruments on the Venus Express mission measured the composition of these escaping particles in the planet's plasma wake. The probe detected hydrogen and oxygen escaping in the exact 2-to-1 ratio of water. This confirms Venus literally bled its oceans into space. Even with a stable orbit, an unshielded planet will eventually be dismantled by the sun's radiation. Earth currently possesses both a magnetic shield and a stabilizing orbit, Yet we are still subject to a thermodynamic limit. The sun's luminosity is steadily increasing, which will eventually overwhelm Earth's environmental systems. This chart models the future relationship between rising solar radiation and atmospheric carbon dioxide over billions of years. Rising temperatures accelerate weathering of silicate minerals, trapping carbon dioxide in rocks. By the 600 million year mark, CO2 levels fall below the threshold required for photosynthesis. At this point, C3 and C4 photosynthesis will fail. The global food web will cease to function as its primary energy source is removed. 1 billion years from now, a 10% increase in solar luminosity will trigger a moist greenhouse effect. The oceans will evaporate completely. Without water to lubricate the crust, plate tectonics will stop, ending the planet's geological cycles. The solar system is temporary. While Earth holds the inner orbits in place, the system is ultimately governed by the inevitable decay of stellar physics.